So in this problem, we're given a situation that looks like this. We have a wheel of radius r that's connected to a rod that extends a length 2r beyond the wheel, and the rod is actually in the radial direction. The rod makes an angle theta with the horizontal and is attached to a mass m that hangs down off the end of the rod, and the other end of the wheel is attached to a mass 2m that hangs directly downward. Now, we're told that this system is in equilibrium, and we're asked, based on that, what the angle theta has got to be. So equilibrium is going to be a really important word, has been a really important word for most of the course, and will continue to be a very important word for the rest of the course. So whenever you see a system that's in equilibrium, this tells you that the sum of the forces on the system, the net force is 0, and the sum of the torques on the system, the net torque, is also going to be 0. So that means the system won't be accelerating, it won't be accelerating angularly, and so basically the system just won't be changing at all. So in this case, we're going to assume that the force at the axle of the wheel is going to completely support the system, so we don't have to worry about the sum of the forces. We do, however, have to worry about the sum of the torques. The sum of the torques has got to be 0, and we're going to find the clockwise direction to be positive, and we're going to have to calculate the sum of the torques about this center axle so that we don't have to worry about the supporting force that's keeping the system in place. So the torque first due to the mass 2m is just going to be 2mr, or 2mgr, sorry. And that's going to be because the force on this mass is going to be 2mg, and that extends up through the tension in the rope to this point, and the distance from the axle to this point is r. The force is 2mg, and the angle between them is theta, and as we all know, sine theta is equal to 1. Now we have to subtract out the torque due to this force. This is going to be mg times 3r. The distance is 3r from this point, because this is the point we're worried about. That's where the tension connects to the rod, which is embedded in the wheel, so when the rod moves, the wheel will move. So we have the force, the distance, and now we need the sine of the angle between them. The sine of the angle between them is actually going to be the sine of this angle, phi, right here. But the sine of phi is the same as the cosine of theta, because theta is what we're worried about. So we're just going to put in cosine theta right there instead of sine of phi. And now we can solve for this. We can cancel out a factor of mgr, and we end up getting that torque is equal to 2 minus 3 cosine theta, since torque is equal to 0. And then we can rearrange this term to get 3 cosine theta is equal to 2. Cosine theta is equal to 2/3. Theta is equal to the arc cosine of 2/3. And that'll be our final answer.